separation, you see that the bright fringes of one should come in the dark fringe of the other. So the contrast, yeah, of the fringes should totally disappear. And so he said, wow, this is a nice experiment because you could measure angular diameter of stars or binary stars with an angular separation, delta, which is equal to half the value of the interfringe separation. And the interfringe separation, you remember, is lambda over B, where B is the baseline. Yeah? So what he did, yeah, he just equipped the 80 centimeter telescope of Marseille, yeah, with such a screen that you see here. And in fact, you can use 2 slits, yeah, instead of 2 holes, because in the Young's experiment, yeah, we've seen that the fringes were appearing when the screen was drilled with 2 holes, but there were fringes. So even instead of having 2 holes, yeah, you make well two slits in the screen. Well, all these fringes will perfectly superimpose over each other. They will be brighter, yeah, and you will be able to detect fainter objects, yeah. So they did that experiment with so Stéphane and Fizeau, and well, the angular separation of the stars they could have resolved, yeah, is for 65 centimeter, yeah, baseline between the 2 slits, yeah, about 0.16 arc second, yeah. So this is a sub-arc second separation, and they observed all the bright stars in the sky, one after the other, yeah, so hundreds of stars, and they never saw a change in the contrast of the fringes, yeah, which means that all the stars have an angular diameter smaller than 0.16 second of arc, yeah. And well, this was not a big surprise because, as you remember, Newton had predicted, yeah, that angular diameter of stars should be of the order of a few milli-arc seconds, yeah. Rather than here, the angular resolution is 160 milli-arc seconds, yeah. So, well, this is of course a big improvement, yeah, over Galileo. So we know that the angular diameter of star, well, he knew that angular diameter of star was smaller than 5 seconds of arc. Now we know that, well, Stéphane and Fizeau knew that the angular diameter of star, yeah, would be smaller than 0.16 second of arc, yeah. Yeah, now an important quantity, yeah, that is being used by interferometrists to, well, quantify, yeah, the degree of contrast you see when looking at the fringes, yeah, is called the visibility. Yeah? So the visibility, yeah, is a maximum intensity of the brightest fringe minus the minimum intensity of the faintest fringe, yeah, divided by the summation of the two, yeah. Okay, now let's assume that you don't resolve a star, yeah. So it's point-like. Well, we know that we would see bright and dark fringes, and that the dark fringe would have a 0 intensity. So if you set here I mean equals 0 in the numerator and in the denominator, yeah, well, you would find that the visibility would be equal to 1. Okay, so whenever you don't resolve a star, you see very bright fringes and dark fringes, yeah, the visibility is equal to 1. Now, in case, yeah, you resolve, yeah, well, a binary star system, yeah, or an extended stellar disk, yeah, of course, the bright fringe is equally bright as the faintest one, yeah, because you don't see any fringes, yeah. So Imax minus Imin is equal to 0, yeah. So then the visibility is 0. So you see, it's a very nice quantity, which varies, yeah, between 0 and 1, yeah. And remember its expression, yeah, because it will come very soon, well, very often, yeah, in the remainder. Okay, now what has been proposed, yeah, in the lecture notes, yeah, is to build your own milli-interferometer, yeah. And well, I guess some of you, yeah, made a try during the weekend, yeah. And with Anna, my wife, yeah, during the weekend, we were also busy trying to make new interferometers with, you know, just aluminum papers that we could borrow from a lady, needles from another one, yeah. And What I'll do now, I will just change the screen, yeah? So I stop sharing the screen and go to another one with you. So, partager l'écran. Yeah. So here is the new screen I want to share with you. And it will be, oh, yeah. So here is a light source, yeah, that we bought for €2, yeah. So a very cheap one, yeah, made in China, unfortunately, yeah. You see that, well, there is a small disk of light, yeah, with a small extension, probably half a centimeter. And what we did, yeah, well, we just hang it, this light source, yeah, you see on the clinch of a door, so that we could observe it, from very far away inside the home, yeah. Then, well, we took a needle, yeah. So this is just to drill in a sheet of aluminum, yeah, very small holes, well, typically with a diameter of a half a millimeter. And you know that to make the holes, yeah, reproducing an optical interferometer, you need to drill two holes, yeah. And it's not easy, yeah, to drill two holes with the same diameter and same, well, a very small separation, linear separation, yeah. So what we did, yeah, we took two needles, yeah, and well, we kind of glued them all together. So you see the two ends, yeah, of the needles, yeah, on the screen, so that when you would drill the holes, yeah, in the aluminum sheet, yeah, each time, yeah, you would get, yeah, two equal size holes, yeah. So this makes life very easy. Yeah, in the past, yeah, we spent so much time, yeah, to try getting two similar holes, yeah, and here, well, it was really very easy to get them. So here you see a piece of aluminum, and we are drilling here single hole in it, yeah. And now we do the same experiment, yeah. We take a sheet of aluminum and drill with a double needle, yeah, pairs of holes, yeah, always with the same linear separation. And so what we did, yeah, we drilled many holes, yeah, well, typically 8 pairs of holes and then 8 single holes, yeah. And then, well, we looked, yeah, with the light source behind, yeah, which pairs of holes and which single hole, yeah, looked the best to us, yeah. So we eventually use a magnifier, yeah, to see. Now here you have a very closer view. On the left, yeah, you see a single hole drilled in the aluminum sheet, and on the right side you see some pairs of holes, yeah, being about equal in size, yeah. Then, well, we cut these pieces of aluminum, but we wanted to make photographs for you, yeah. And so what we did, yeah, we prepared a screen, yeah, that we would set in front of a photographic camera. So here you see it's a cardboard, yeah, and we just cut, yeah, a circular piece of cardboard. Now in the center, yeah, we will drill, yeah, a small square aperture, yeah. And here you see after cutting, yeah, the inside square aperture. Now, these are the two pieces of aluminum, yeah, on the left side with a single hole, and on the right side, you better see, yeah, the two holes drilled in the very small sheet of aluminum. So the size here is about 1 by 1 centimeter. Yeah? So what we did then, we glued, yeah, these pieces of aluminum, yeah, on two circular cardboard, yeah, with a square aperture, yeah, in the middle. So you see on the left, yeah, single hole aperture, and on the right, double hole aperture. Here is the other side, yeah. You see, we have two screens. Now, what you do with it, yeah, well, you look at the distant light source, yeah. Well, here is Anna, yeah, looking whether, yeah, she could see, well, in this case, yes, yeah, iridescent, yeah, and while using the double holes, you would see, yeah, the fringes, of course, yeah. But since we wanted to show them to you, yeah, we took our photographic camera, Well, I have no cell phone, as I told you, and I'm sure that it would also work with a cell phone and maybe just a, a mere magnifier in front of it. Yeah. So there is room for experimentation, and I hope to hear from you. Yeah, during the next lecture. Here you see we just put the two-hole aperture, yeah, in front of the objective of the camera. Here is a closer view. Then here we set the camera, yeah, at some distance. Well, the distance is not too big because the room, yeah, we were experimenting, yeah, is not a big one. The distance was 3.5 meters, yeah, from the bright source of light. Now, first what we did, yeah, well, we removed the aperture, yeah, and took in the automatic mode, yeah, a direct image of the light source, so that we would have a good, well, with the autofocus, a good estimate of the distance, yeah. Then we came back in the manual mode, yeah. Then we took first the single hole aperture, put it, yeah, on just in front of the objective of the camera, and took the picture. And here is what you see. So you see in the middle, yeah, the central dot of light, which is a central part of the airy disk. And you may guess, yeah, around it, yeah, well, a minimum and then some scattered blue light, yeah. Well, the next image here is a longer exposure, and well, you see a very nice airy disk, yeah. So maximum concentration of light, yeah, in the central part of the airy disk. Then we see a first ring, yeah, and some dispersion of the light, because you know that the airy disk size depends, well, it's proportional to the wavelengths, yeah. So of course, shorter is the wavelength, yeah. Smaller should be the size of the first ring, and it's what you see here, yeah. First ring inside is blue, and a bit further out, yeah, is redder, yeah. Well, here is still a deeper, yeah, image, and well, you see there are imperfections due to the fact that our hole is not perfectly circular, yeah. So it was made with a needle, yeah, and this is the best we could do. Now, after we used we use a screen, yeah, with a two-hole aperture, put it, yeah, in front of the objective of the camera, and here you see the fringes, yeah, very nice fringes, yeah, which angular separation, yeah, is lambda over b, where b is the baseline, and well, the baseline is probably about 1 millimeter in this case. You also see, yeah, the trace of the airy disk, yeah, around it, yeah, where you see it better in this image. So we see still the airy disk, yeah, and with the fringes. Now, what you see is that the visibility, yeah, is not one, yeah. We don't see very dark fringes, yeah, and the reason is simply that we were not, sufficiently distant from the light source, so we are partly resolving it, yeah, and we have that information, yeah, in this picture. Okay, so now I will stop sharing my screen. Okay, and go back to the PDF presentation again for a short time before listening to your questions. Yeah. So this experiment, yeah, is well described, yeah, in the lecture notes, yeah, and we invite you, yeah, to try to build your own micro interferometers, to send us some pictures, yeah, and well, Prakash just suggested, yeah, that we would well take into account, yeah, your progress work, yeah, for the certificate, yeah. So we would like, yeah, if you build your own micro interferometer, you've seen it's very easy, yeah, to send us a direct photograph of it, yeah. Then, well, another photograph showing us, the shape of the holes, yeah. So you may use your cell phone, yeah, to make a photograph and magnify a little bit the image, yeah. And then, well, if you can, try to take a photograph, yeah, of the fringes, yeah, and send us a photograph, yeah. And we'll take all of that, yeah, into account, yeah, when evaluating, yeah, your involvement, yeah. Now, when the lecture notes, yeah, we just show that Michelson and Pease, yeah. Well, first Michelson, yeah, was clever enough, yeah, to use a 2070 centimeter or 30 centimeter telescope, yeah, in trying the FISO experiment, yeah, on the satellites of Jupiter, yeah, and well, with a baseline of about 25 centimeter, yeah, it could resolve, yeah, uh, the size of the satellite, yeah, which was a nice demonstration that the principle works, yeah. And then with PIS, yeah, where they just set a beam, yeah, 7 meter long, yeah, on top of the Hooke telescope, which is a 2.5 meter telescope here at Mount Wilson Observatory in Pasadena in California. And they tried, yeah, to, well, measure the angular diameter of stars, yeah. And they knew that Betelgeuse, yeah, which is Alpha Oriolis, was a red supergiant, yeah. And also, it is at a distance of about 650 light years, yeah. Well, at the linear size, about 400 times, yeah, the size of the sun, in that they would have a good opportunity maybe to resolve it, yeah. And indeed, yeah, this was the first star they could resolve. So the angular diameter, yeah, they measured was 47 milliarcseconds, yeah, which was, of course, a fantastic result, yeah. Well, today, if someone, yeah, would have achieved, yeah, such a, well, novel measurement, yeah, he would have got the Nobel Prize, of course, yeah. Okay, so that's all, yeah, as far as I'm concerned. And now, well, we will listen to you, yeah, if you have questions, or if you already tried to construct your own micro interferometer, yeah, where you could share with us, yeah, your experience, yeah, even difficulties, yeah, yeah. Well, if you had some, yeah. So the floor is to you.
Okay, so anyone who has any question regarding the content that was covered right now, or any of the previous content like the first lecture or anything related to the course, you can ask a question. You just have to raise your hand and I'll allow you to unmute your mic. The first question I think is from Vikram Pradhan.
Mm-hmm.
Okay, thank you. Thank you, Jean. I have a question. During the FISO experiment, you showed that they could not get better fringe separation than 0.16 arc seconds. So is it right that they did not observe any binary stars? I mean, those stars are their linear size is too small. What is the reason? I could not get it, in fact.
Yeah, well, I fully agree with you, yeah, that they could have tried, yeah, to resolve, yeah, some known spectroscopic binary, and probably they would have succeeded, yeah. Well, they could have also tried, yeah, to resolve the angular size, yeah, of the Galilean satellites, yeah. So I mean the satellites of Jupiter, yeah, and they would have succeeded, yeah. So it's a very pity, yeah. Well, I felt so sorry too, yeah, that well, finally the idea came from them, yeah, and that they didn't get any result, yeah, and that Michelson, yeah, had the bright idea even to use a very small size telescope, yeah, 30 centimeter telescope, and to try to demonstrate, yeah, that this experiment is working, yeah, and he did that on the satellites of Jupiter, yeah. So I feel so sorry for FISO and his collaborator, yeah. Yeah, because as you mentioned also, yeah, later on, yeah, well, Michelson and Pease and other collaborators, yeah, resolved a lot of many binary stars, and so it should have worked also for FISO and Stefan, yeah. But yeah, that's the way, yeah. they really wanted to resolve the disks, yeah, of the stars, yeah, and they didn't think about resolving anything else, yeah, which is a pity. Now, well, a very nice experiment, yeah, that we should propose to those who have the opportunity of having at home, yeah, or binoculars, yeah, or a small telescope, or a big telescope, yeah, is to put a screen, yeah, in front of the aperture and to drill holes, yeah, with adequate size, adequate separation also, yeah, to resolve, yeah, some of the objects in the sky, like, well, it could be Jupiter itself, yeah, it could be, well, another planet, it could be the satellites of Jupiter, yeah. So this is very easy to do and a very nice experiment, yeah, to be carried out, yeah, with students, yeah. Now, if some of the participants, yeah, also want to do the following experiment, yeah, as I said, yeah, if you use your screen, so I will just take a, yeah. So here is a, yeah, here is a screen, yeah, yeah, with the two holes, yeah. If you would set the screen, yeah, very distant from the light source, yeah, well, we would have seen, yeah, very clear fringes, yeah. Well, as we go closer and closer to the light source, yeah, where the contrast, yeah, will vanish and the visibility eventually will get to zero. And what you could try, this is a very nice experiment, yeah, is to try to get images, yeah, and try to measure the visibility and plot, yeah, the visibility as a function of the distance, yeah. And you would have one way to directly measure, yeah, the diameter of the side of the light source, yeah. So anyone, yeah, who wants to bring some results, yeah, of after experimenting, you know, with this very simple experiment, yeah, it would be fantastic, yeah. So did I answer your question, Ikram?
I think he is muted.
Yeah.
Okay, the next question is from Pallav. Go ahead, Pallav.
Yeah, you should unmute.
We can't hear you yet. Pallav? Okay, we'll move on to Satyam Roy.
Hello, sir. My name is Satyam Roy, sir. My question is, sir, the intensity of Yeri pattern also follows the Fraunhofer diffraction. Can you tell me something about, sir, Fraunhofer diffraction, sir? How does it come?
Yeah, so this is the subject of two more lessons, two more lectures, yeah? So just be patient. Otherwise, I would do lecture number 4 now, yeah? So this will be addressed, yeah, in the lecture number 4, I think, yeah? Okay?
Okay. So next question is from Deepak Raj. Deepak, go ahead.
Hello, sir.
Hello.
So I have this question about this coherent nature of light. So as it is the topic to be covered, I have a doubt if I should ask the question, but I'll ask anyway. So in this experiment with double slit and single slit, what we have, what we should have is a coherent source, right? Coherent same light source with the same polarization output. So if it is not, then we cannot observe the fringes, right? So in case of the stars, we can say it is not a coherent source, right? Then how can we observe these fringes? That is a question.
Yeah, sure. Yeah. So, of course, here also, yeah, in the full answer, yeah, to your question, yeah, will be given, yeah, during the next lectures, of course, yeah. But to be very shortly, yeah, I would mention the following. In the two-slit experiment of Young, yeah, well, we are using a very distant source, yeah. So there is a plane wave, yeah, coming on the screen, and monochromatic light, yeah. Now, in the experiment, yeah, that you may reproduce at home, your light source, yeah, is not monochromatic, yeah, and it's not infinitely long from you, yeah. So, well, it's very easy, yeah, as I said, yeah, to get very, very far from the light source, yeah, and to see that you will see the fringes with a very big contrast because the light is infinitely far away, yeah. Now, concerning the monochromatic aspect of the light source, yeah, what you have seen, yeah, on the photographs I showed is a chromatic effect, yeah. So indeed, you get an airy disk, perfect airy disk, if you work, yeah, within a very narrow spectral band, yeah. Now, if your spectral band is not narrow, as shown here on the photograph, then you get chromaticity, yeah. So the light is being dispersed, yeah, chromatically, yeah. And it's what we observed, yeah. So you've seen, yeah, the blue disk, yeah, was at the narrower or at the smaller radius, yeah, than the red disk, yeah. So it still works, yeah. So we will relax, yeah, all the, would say, assumptions in the Young's experiment, yeah, namely that, well, the light source, yeah, is not infinitely far away from us, that it has a finite extension. Then we will relax, yeah, the assumption that it is not monochromatic. So the next lecture, yeah, will address that point very specifically. We will work with a quasi-monochromatic light, yeah. So it means within a narrow spectral band, and you will understand why it still works, yeah, and why even with white light, yeah, you still see the fringes, yeah, in the Young's experiment, yeah. So, well, I think I've partly, yeah, answered your question, but with very rigorously, yeah, it will be answered, yeah, during next lecture and still the other one. Okay?
So, but shouldn't the source be in phase? I mean, the source approaching the slit should be in phase, right?
No, no, because, well, a star, yeah, is an infinite number, yeah, of incoherent light source, yeah. But now, okay, but of course, each single one, yeah, is a coherent, yeah. So if it is infinitesimally small, yeah, okay. And now you know that for each of them, yeah, you would get a airy pattern in the, well, in the focal plane, yeah. And so if you don't resolve the star, they are all superimposed and amplified, yeah, and you still see it, yeah. This is the reason. But wait, yeah, until we go, yeah, to the two next lectures, yeah, and then you will understand, yeah, why, yeah, rigorously it works, yeah, yeah.
Okay. Thank you.
Yeah.
Okay, Pallab, are you able to access your microphone?
Yeah, we cannot hear you.
Yeah, Suman, you can ask your question.
Okay. Hello, sir. Sir, I want to ask that in the, from that images you show for that experiment, in the camera, in the lens, there is also already an aperture control is there. If I put the aperture minimum, can we see the airy disk pattern instead of putting a single hole in front of the lens? Just by reducing the aperture, can we see that?
Yeah. Okay. Well, in principle, yeah, you could see it, yeah, if you would have a sufficient resolution, yeah, in your with your CCD, yeah. So pixel size, yeah, small enough, yeah, to cover the airy disk. And if the pixel size is too big, yeah, well, the airy disk will just fall into one pixel and you will not see it, yeah. So you agree that bigger is a whole aperture, yeah. Smaller will be the angular size, yeah, of the airy disk, of course, yeah. And even if you set, yeah, to the minimum, well, well, the size of your aperture, it will still be too big, yeah, to be seen, because you'll be lacking, yeah, resolution on your detector, yeah. So the pixel size will not be small enough, yeah. It's okay. Did I answer your question?
I think we muted it.
Yes, sir. Yes, I got
Yeah.
my answer.
Mhm.
Okay.
Okay. Any other questions? I think Pallav is still not able to.
Yeah, Palab is
Yeah,
raising.
hello.
Yeah.
Am I audible now?
Yes,
Yes.
you are. Go ahead.
Okay. Thank you for this lecture. So after first lecture, I have tried to set up my own interference experiment using laser torch. But instead of that aluminum foil paper, I have used normal paper, normal white page. So it was not working at all. So then my question is, should I have to use only the aluminum foil to do it? And what is the
No,
function of the
no,
aluminum
no, no.
foil?
I don't think so. Well, I think if you would use, yeah, cardboard, yeah, which is thick enough, yeah, so that it would be, it would remain opaque, yeah, outside the hole, yeah, it should work, yeah. Maybe now the aluminum, yeah, well, has the advantage that it's totally opaque outside the hole, yeah, and well, the hole is a perfect transmission, and it works very fine, yeah. But just try with a aluminum sheet, yeah, sheet of aluminum. So this is just aluminum paper used, yeah, in the kitchen, yeah. It's nothing
Yes.
fancy, yeah. You may buy it, yeah, for well, very low
Yes.
price.
Uh,
Yeah,
yes,
but
I'll try it again. Thank you.
yeah, try your experiment with a laser beam, yeah, and well, be careful with your eye, yeah, because I would not look directly, yeah,
Yes.
through the hole, yeah, at a laser beam, because it could damage, yeah, your eye. So be very careful. I would only maybe try to take a photograph, yeah, but not directly look at it, yeah. Be careful, yeah.
Yes, sir. Yes, sir. Definitely. Sir. Thanks.
Yeah. So we remind everybody, yeah, that try to set up, yeah, a small experiment, and well, probably if you have some new ideas, yeah, on how to use those mini interferometers, yeah, well, your ideas are very welcome, and if you have some results, yeah, we will be very impatient to see them, yeah. Yeah. Maybe, well, something I should say, yeah, it may bring some nice ideas to some of you, yeah, is that if you could disperse the fringes, yeah, with a small prism, yeah, well, you would get information, yeah, on the slit separation, well, the fringes separation as a function of wavelengths, yeah, and this is actually used, yeah, in some of the modern observatories, yeah, that they work, yeah, within a narrow spectral band, but still after, yeah, they are dispersing, yeah, the light, yeah, to get information at each wavelength. And so, well, it's very interesting, but I'm sure that it should be possible to do it, yeah, if anyone has a small prism at home, yeah, to try to set it in the experiment and try to take some pictures and to show them to us, yeah, would be nice, yeah. So it's possible to do a lot of nice things, yeah, with this very straightforward experiment, yeah. So we really hope that many of you, yeah, will have the chance to see the fringes, because you will see it brings a lot of joy when you see them.
Yeah. Okay. There was a question, I think we covered it last week, but there's this question on using two different size apertures telescopes for an interferometer.
Yeah. So, well,
Whether
what
one
I,
can use.
yeah, well, what I would suggest, yeah, is that you try to drill, yeah, two holes one which is a little bit bigger than the other one, yeah, and see what happens compared to the situation when the two holes have equal size, yeah. Now, well, to answer your question, yeah, we will make a numerical simulation in one of the next lessons, yeah, addressing that point, yeah. So we'll take two apertures with two different sizes, and we will look, yeah, uh, how the fringes, yeah, should be observed, yeah. So I don't want to give another answer now, but it's absolutely possible, yeah, to use to make interferometry with two telescopes which apertures have different sizes. Yeah, absolutely. Yeah.
Well, there's a very general question. Why do the separation between the double slit and the source matters for the experiment? But that's what we derive in the course, right?
Yeah. Why do the separation between the double slit? Yeah. And so we are for the experiment. Why do the separation between the double slit and the source matters for the experiment? Yeah. Yeah. So just to remind you what's going on here. Why the distance to the source matters? Yeah, it's because when you get closer, yeah, the angular size of the source gets larger. Yeah, so it's easily more easy. Well, it's easier to resolve. You agree? Yeah. So if the visibility gets to zero when you resolve the source, it means that when observing a light source, yeah, and you get closer and closer, yeah, where the fringes should disappear. Yeah. Now, why the baseline, yeah, is important? Yeah. Well, bigger will be the baseline. Yeah. Higher will be uh, the resolution power, yeah, of your instrument. And it means that larger will be the separation between the two holes. Yeah. Smaller will be the interfringe separation. Yeah. So the fringes will be closer and closer. So we'll get a higher angular resolution. Yeah. So then it will be easier, yeah, to resolve the source. So if you're at the same distance, yeah, using two interferometers with two different baselines, well, very likely the interferometer with a long baseline, yeah, will show you fringes with a zero visibility rather than the well the screen, yeah, with a smallest baseline, yeah, will not have enough angular resolution, and then you will see very distinctly, yeah, fringes, yeah, yeah. So this is just what Fizeau and Stefan had in mind, yeah, and this is what Fizeau, yeah, first observed in the laboratory, yeah, that whenever at the same distance from a light source, yeah, he would use two different interferometers, one with a bigger angular, well, with a bigger baseline, would look at the source, well, you would see no fringes, yeah. While using the one with a very small separation, then you would see the fringes, yeah. Then you also observe that when using the same interferometer, mini interferometer, and getting closer to the source, well, it appears to you with a bigger angular size, so easier to resolve, so the visibility gets to zero. Yeah. So just go through the two first lectures, yeah, and this will be very clear. You know, it will become very clear in your mind. Yeah. So maybe the next question I see.
There's a question from Sanjay.
Yeah.
He asks, um, so when the binary stars move together towards or away from each other, the fringe separation also changes. Can this be used to find relative velocity of binary stars or rotation?
Yeah.
The binary or rotation velocities.
Yeah, yeah. No, it will give you no answer at all, yeah, on the relative velocity or on their velocities, yeah. For that, you would need to use a Doppler effect, yeah, and so you would need a spectrograph behind, yeah. So what you would just see when the binary stars, yeah, well, as a changing configuration, is that their angular separation, yeah, is changing as a function of time. And this is very important information, yeah, to fit, yeah, the trajectory, but it should be later combined with the radial velocity measurements, which should come from another experiment, of course, yeah.
There's a question from Zeng Hui. Why do the two lights from the two holes or two telescopes are coherent? Can they have different phases?
Okay, well, yeah. As I said already last time, yeah. Well, if you have two apertures, yeah, and the phase is a bit different, which will certainly happen, yeah, because the layer of the atmosphere, yeah, just above one aperture, yeah, will not be the same, yeah, as the layer of the atmosphere just above the second aperture, yeah. And what will be the consequence of that, yeah, is that the fringes, yeah, the focal plane, yeah, will change their position, yeah. So they will go from one place in an erratic way, yeah. And well, to integrate those fringes, yeah, you would absolutely need what is known as a fringe tracker, yeah. And of course, I speak about that, yeah, in some of the next lectures, yeah. So, well, there are many questions, yeah, to which, yeah, the answers, yeah, will naturally come, yeah, during the next lectures, and this is a good reason for you to attend the next lectures. Yeah?
Okay, good. Does anyone else have any questions?
Yeah, well, I see here, yeah, sir, will it make any change if we use an uneven cardboard and make two holes? Which depths will differ? Yeah. No, well, in fact, yeah, well, the depth of the, yeah, the depth of the holes, yeah, doesn't matter at all, yeah. What is important, yeah, is their size and their shape, yeah. So this is one question I saw. Then, okay, so why do the two lights from the two holes or two telescopes? Okay, that we answered. Okay, I don't see any more questions. No. Oh, hello, sir. Is the experiment affected by temperature? Well, if you know, you warm too much, yeah, the sheet of aluminum, probably there will be some dilatation. The baseline will change, yeah, and you know the interfringe, yeah, separation should decrease, yeah. But of course, I mean, at the VLTI, so it's a very large telescope interferometer in parallel. They control very much, yeah, the temperature in the tunnel where are the delay lines, yeah, because indeed, yeah, it could have some influence, yeah. So for the millimeter interferometer, well, it will have no effect, yeah, probably, but for real interferometers, yeah, it's very important, yeah, to keep very stable, yeah, the temperatures because it may change the length, yeah, in the path of the different light beams, and this has an effect, of course, yeah, on the results, yeah. Yeah, so we are very impatient, yeah, to see your, well, maybe some of your results, yeah, appearing in the forum, yeah, which is widely open to everybody, yeah. And if you have nice pictures, yeah, I think you may probably post them there or send them to us. I don't know. Maybe Prakash can say something on that. Yeah, it's the best way to share, you know, results and photographs.
Oh yeah, for the experiment, we will set up a separate link in the course webpage for it will say something like an assignment or extra credit activity. And you can, it will have a way to directly upload your images. Just make sure that the images are less than, close to 500 kilobytes or maybe less than 1 MB. We don't want very huge file sizes.
Absolutely, yeah. And well, today, yeah, I will send to Prakash, yeah, the PDF file, yeah, with all the photographs I showed, you know, when we were preparing, you know, our screens with a single and the two holes. and so that it will become available to you. Yeah, we'll also set online the time lapse of the comet so that you have a chance to see it under better conditions. And we are very eager to see your efforts in experimenting with sheets of aluminum and holes and or with screens just set in front of a bigger aperture, which could be binoculars or a small telescope or a bigger telescope. So any more questions? Oh yeah, I see
There are a couple.
one raised hand. Yeah.
Oh, there's one raised hand too. Okay, Ram, go ahead, unmute, and you can ask the question.
You should unmute yourself. Yeah, you're muted.
Yeah, Ram Kishore. It shows.
Yeah, Ram, you're still muted. Yeah, you should try to unmute.
Ram Kishore, are you able to unmute yourself?
Yeah. It disappeared now.
Yeah. Try to find it. Okay, Dodi, go ahead. Dodi, you have a
Dodi,
question?
you should unmute. You should unmute yourself.
Yeah, go ahead.
Hello?
Yes, we hear you.
Hello? Hello? Okay, last lecture, from the last lecture, depending on these interferometers, I remember you said that due to the limitation of technology, so far the maximum distance, the maximum diameter for telescope is only 40 meters. Now, in case maybe technology allows to use a telescope of more than 40 meters, so there will be any need of using maybe many telescopes, or maybe this technology will replace the use of using many telescopes. So we just use one big telescope whose diameter will be more than 40 meters.
Well, presently I'm not aware that, technology would allow to build telescopes with a diameter larger than 40 meters. Yeah. Now, well, many people would like working, on the exoplanet, science, would like to resolve, those very tiny dots of light, around nearby stars, and even to probe, the atmosphere, to find what is chemical composition, etc., etc. And for that, you need even baselines, which are in the optical or near infrared, of the order of 10 kilometers. So you see that interferometry will always be very appropriate for some scientific goals, because you'll never build a telescope with a 10-kilometer size diameter. So all these different approaches are just complementary and not exclusive. So right now, even getting to a 40-meter telescope is going to be a very big challenge. And I'm not certain that this will be achieved within the next decade. But we will see.
Okay, thank you.
Yeah.
Okay, thank you.
Okay,
there's a question from Sanjay on the chat window, which says about using the Galileo's method of using a wire to measure the diameter of stars and planets. Mm-hmm. And he says that he tried it, but there's some diffraction from the side of the wire. He's asking how to avoid this when observing moon's diameter.
I see. Yeah. could he tell us, I mean, what was the size of his wire?
Sanjay, can you raise your hand? Or could you unmute yourself? I just gave you permission. Oh, he just says in the chat window millimeter. Is that the diameter of your wire? 1 millimeter? I think. Yeah, I don't know. He's not able to turn on the mic, but he says millimeter.
Oh, the millimeter, yeah. And so he's observing, yeah, some diffraction effects, right?
Yeah, apparently.
Diffraction effects, yeah. So, well, I try to think about, you know, this question, yeah, and to see whether, well, I need to make some calculation to see, you know, what is importance indeed, yeah, of the diffraction effect, yeah, and how you could overcome that, and then just to see whether indeed Galileo, yeah, experimented the same difficulties or not, yeah. But it's interesting, of course, yeah, yeah, because it's true that you could get maybe some source of diffraction, yeah, from the starlight, yeah, on the wire. But I need to look at the problem, yeah, well, very carefully, yeah, before giving any answer. Okay, so we'll talk about that again, yeah, during the next lesson. But nice, very nice if you tried, yeah. And could you tell us, I mean, at which distance from the wire, yeah, you observed those diffraction effects? Because this is of some importance too. So could you hear my question? Yeah. So I was just wondering, yeah, at which distance, yeah, from the wire, yeah, you saw some diffraction effects.
Jupiter at a distance of 20 centimeters.
Yeah. Oh, I see. So it was observing Jupiter, yeah, at the distance of 20 centimeter with a wire, yeah. So what I propose, yeah, is to attempt the same observation, yeah, using a wire with a diameter of 1 millimeter at a distance of 20 centimeter, yeah. And I'll come back to you, yeah, during the next lecture, yeah. But interesting, yeah. If more of you, yeah, would like to attempt, yeah, that experiment, it's interesting, yeah. Why not? Yeah. Yeah, Jupiter, well, is in principle visible right now, yeah. Well, it must culminate, yeah, around midnight, something like that, yeah. Okay, nice proposition.
Yeah. Okay, I think we can stop it here. Right.
Okay. Very fine. Yeah. And so remember all, yeah, that there is a forum and that your inputs, yeah, well, are important to us, yeah. And yeah, if you have any interesting results, yeah, just share them with us, yeah.